In this video, we are going to go over some parts per million calculation practice problems. I'm going to do one with you, and then I'll set up the harder ones on the back so that way everyone can do them. So let's start with number one. It says a pharmacist wants to prepare a medication that has an active ingredient of 50 parts per million. So whenever we set these up, always write your formula out. Again, I write 10 to the 6 because it's shorter than writing a million. So 50 is my parts per million, goes there. The final solution should have a mass of this many milligrams, so that's my solution. Remember that if they give you a number like this, the decimal is always at the end, even if it is not written in, especially if it's not written in. If it is written in, then it is where it is. There's nothing you can do about it. And they want to know how much active ingredient. Now, if I notice, they say how much active ingredient is required. So they didn't mention a unit. So since the bottom number is milligrams, that means my top number is also going to be milligrams. If they said how many grams would it be, well, then I've got two options. I could get my answer in milligrams and use King Henry to convert, or I could convert my solution number before I did the problem into grams, and then my X would be in grams as well, and then I'm done. So you either convert before or after. It doesn't make a difference with this type of problem, but you would have to convert. In this case, they didn't mention that, so I don't have to worry about it. So first step's going to be to distribute. I'm going to do the math on the first one. So distribute the million to the top number so you get this. Then you make two fractions and cross multiply. And you end up with make sure I have the right amount of zeros here. Then divide by a million on each side. And there's my final answer. So these numbers can get large, but again, that's because you're multiplying things by a million, and if you're using milligrams, they can be very large, they can be even larger, so the numbers can get large, but if you follow your way through, it shouldn't be too big of a problem. Let's jump to the back, because these can be, actually, let's start with number 4. I'm going to mention some stuff on the questions where students tend to have a harder time. So number 4 is ammonia in the fish tank problem. So the concentration is 250. So it says an ammonia concentration of 250 or more is lethal to fish. That's not the concentration of this particular tank. It's saying if this number is over 250, dead fish, so, or more 250 or higher. So the fish tank contains 375 kilograms of water and 15 grams of ammonia. So you're going to have to make sure, be aware those units don't match up, so you're going to have to make them match. Calculate your PPM, and then if it's under 250, we get happy fish. If it's over 250, unhappy fish. And so that's what the 250 is there for. It's just to giving you the point at which the ammonia levels would become toxic to the fish. And so that's all you're doing for number 4. It's a regular problem, and then you're comparing it to the 250 mark. When we get to the last 3, they have stars on them. They're not that much harder. They just require you to do a little extra work. So for number 6, it says a 10 kilogram solution of water contains 0.005 moles of sucrose. Here's the formula for sucrose. What's the concentration? Well, we need to know grams. We need to know grams or kilograms, right? Because we're doing massive solute over massive solution. So this is my mass of my solution. Whether I keep that in kilograms or grams, it's up to you. But I don't have a gram number here. But if I know moles, which I have, and I have a formula so I can calculate my GFM, I can use the mole formula here. To solve for grams. And then once I have those grams, that's the solute. This is my solution right over here. and then I can calculate my parts per million. So it just requires one extra step. Yes, you can use a mole formula with a parts per million formula, and even a molarity formula for that matter. They can all be used together. They're all using very similar units. For number 7, it says, so here's my milligrams of solution. The concentration is 63 parts per million. How many moles are in that? Well, this is the same two problems, but used in the, this is the same problem as number 6, but used in the reverse order. So in other words, I have my milligrams of solution, I have my parts per million, solve for milligrams of solute. That solute is the KNO3. So once I know how many milligrams of solute, aka KNO3, I can then use the mole formula again. And be aware, this is going to be KNO3 for my GFM. And I'm going to solve for, what do they want here? How many moles? So they want moles. So the milligrams of solution is going to have to be converted into grams, plugged into here, used with the mole formula, and then I'll get moles. So I'm using the same two formulas, the parts per million formula and the mole formula, the same way I use the molarity formula and the mole formula. I'm just swapping the molarity formula for the parts per million formula in these two equations. So there's nothing harder. The only issue is just making the link, understanding that you have to use those two formulas together. So I'm going to let you do the rest, but there it is. And then the last part, this one throws everybody off, but if you listen to the notes, I mentioned this already. It says a saline solution, the saline solution bags used in hospitals to replace body fluids through IVs are 5% saline by weight. A saline bags are actually filled with salt water. I don't know if that's 100% true, to be perfectly honest, but whatever. It's a chemistry problem. We're not saving anybody's life with this. What is the concentration of salts in parts per thousand, keyword there, in a 1.5 kilogram saline solution? So what they're telling you here is, so I'm going to write part PPT for parts per thousand. But notice it's times 1,000 because it's parts per thousand. So that's the first thing. And so what they're telling you here is that your 1.5 kilogram solution, keyword here, it's the solution. So the solution is 1.5 kilograms. And then they tell you that 5% of that solution is salt. They say saline, but salt. So 5%, 1.5 kilograms is my solution. 5% of 1.5 kilograms, which I'm going to leave you to solve, is the salt, is the actual salt itself, because they said 5% of it by weight. So 5% of 1.5 kilograms, or you could say 5% of 1,500 grams, because it's the same thing, just I converted the units. And what you're ultimately going to solve for is the concentration in parts per thousand, but you have to go that extra step and figure out what 5% of the solution weight is so that you can get the solute's weight and do it that way. So that should be everything here with this one, with these problem sets. I will have an answer key where I give you just the final answer. You're going to have to show, obviously, just like always, every single ounce of the work in order to get credit. If you skip steps, I'm just not going to give you credit on that.